Alright, so we've been talking about centroids. Why do we care about centroids? We care about centroids because we care about distributed loads. So distributed loads are some sort of loading that varies based upon its location. So say, for example, you think of some snow on a roof. If there's sections of the snow on the roof that is 4 feet high versus some sections of the snow where it blew away and it's only 1 foot high, then you're going to have different weight. You're going to have a different distribution in how the weight presses down on the roof over the area of the roof. So that'd be what we call a distributed load. So in 2D, a distributed load is typically given by some sort of plot function of the load per unit length. Denote that here by W. So again, typically speaking, we're talking some force over a length, newtons per meter, pounds per foot, pounds per inch, so on and so forth. And then basically, the way you calculate is the total load is just taking that load line and calculating the area underneath that load curve. So we figure that out by integrating that load line over the area. But of course, if we're looking at a tiny little slice there, the dW, then the W term here the W term is the function here, and then the dx is the tiny little slice. So it'd be basically equivalent to the area under that curve. So we can calculate that fairly easy. The reason we talked about the resultants the reason we talked about the centroids is because the resultant passes, if you replace this distributed load with a resultant that has this weight or this amount of force, then as long as it passes through the centroid of this area, then it is an equivalent force system. So essentially what we're saying there is, as long as it passes through there, when you take the combination of all the tiny little forces that make up this distributed load, as long as it passes through the centroid, then the net moment is zero. So you're not going to be getting any net moment there. So you're good to go. So some common distributed loads. Probably the one you're going to see most often is a uniformly distributed load. So the total weight there is just the W times the L. We've got a triangularly distributed load. Sometimes they'll give that in terms of a Q naught, which is just the distributed load at its maximum here. So calculate that just, base times height divided by 2, same way we do any triangle. And again, the centroid, like we saw, 2/3 of the way from the pointy tip to the other end, or 1/3 of the way from the fat end to the pointy tip. So let's work through an example of this. So we've got this beam supporting a distributed load that's shown. And we need to figure out what the equivalent concentrated load would be, and thus what the reactions at the supports are. So we'll go ahead and copy that into OneNote. Alright, I'm going to move this over here. Okay, so
So we have, in fact, so we got this shape here. That's not a uniformly distributed load, and it's not a triangle. But what it is, it's a combination of the two. So essentially, we can treat it the same as if we have a uniformly distributed load of the 1500 newtons per meter, and then a triangularly distributed load of this 1400 minus the 1500 to give us that area here. So that times the so that is the height of the triangle. The base is still the base is the 6 meters for both of them. So we'll just draw a quick free body diagram for this thing as well. And actually, I'll switch from fuchsia. Now let's move that down a bit more. Okay, so I'm gonna draw in here. Here, I'll put the uniformly distributed point in green. I didn't realize I'd change this to color my box there too. Oh well. So that one will be the 1500 newtons per meter. And then let's have a blue one here. So I'll have a blue. And we'll have our supports as well. So we've got a roller connection here at A and a pin connection at B. So we know that you want to black. There we go. So we know that we got some sort of Y reaction at A. We know at B we're going to have a Y reaction. And we're going to have an X reaction, I suppose. Oh yeah, I forgot to define my coordinate system. So let's go ahead and do that. X, Y, and Z. So we'll go ahead and do that. First things first, delta sum of the forces of X equals 0, which is equal to Bx. Let's cross that out. So we want to take these forces, these distributed forces, and replace them on the graph with an equivalent concentrated load, because otherwise we can't really figure out what's going on at our supports. So for the 1500 newtons per meter uniformly distributed load, well, we've got 1500 newtons per meter. And we got 6 meters, which means that we will have a force smack dab in the middle there of 9 kilonewtons. So we know it's smack dab in the middle because the centroid of a rectangle is smack dab in the middle. So that is located at a point 3 meters from either side. I'm just going to use the one there, the one on the left, because we're going to probably need the one on the right. Need the space for the one on the right. So we've also got our our linearly varying load in the blue here. Put a box around that there. So what's the magnitude of that? Well, again, we're looking at the area of the triangle. So the magnitude there, that's going to be our 3000 newtons per meter times
the 6 meters divided by 2, which I guess that'll work out to be, that'll also work out to be 9 kilonewtons. Which we can tell because taking this and divided by 2 gives us that, and we're multiplying by the same length. So we've also got 9 kilonewtons. Where is it acting? So again, if we start from the fat end of the base, moving towards the point, start from the fat end, move towards the point, then we're going to be acting 1/3 of the way there, so it'll be 2 meters. So it'll be right about here. 9 kilonewtons. So we got that at 2 meters, which means that we have 1 meter in between those two. If we want to simplify things a bit further, we've got 2 forces that are equal and acting in the same direction. So what we can do is we can just take those and replace them with a single force acting directly in between the two. So I'm going to go ahead and do that. 18 kilonewtons. That is 2.5 meters from this end, and it is 3.5 meters from that end. So we got that. We've got our AY, and we have our BY. So, in order to figure out our reactions, we just need to go ahead and do what? First thing we should probably do is take a moment. Take a moment about, let's go with a moment about B. A moment about B. Alright, so obviously we're working in 2D, so all the moments will be in the z-axis. It will be about the z-axis. And what we want to get here is we want to ensure that that's equal to 0 because it's a static equilibrium problem. So 0 is going to be equal to, well, we got the 18 kilonewtons. And that'll be times the 2.5 meters between the point it's acting at, 2.5 meters, and again that's going to be positive. Oh, sorry, no, with that. Yeah, that's right. That's going to be positive because it is acting. It is applying a counterclockwise rotation to the object in question relative to B. So we got that. And then we're going to have the AY reaction minus AY times 6 meters. And that is obviously going to be counteracting the positive moment. So it's applying a clockwise rotation, which is our negative moments. So we subtract that value there. That lets us solve for AY. That's going to be equal to 18 kilonewtons times 2.5 meters divided by 6 meters. Meters cancel out. 18 times 2.4 times 2.5 divided by 6. That gives us an AOI of 7.5 kilonewtons. And the next thing to do would be to get the sum of the forces in the y direction and have that equal to 0. So we got BY, we've got AY, and we've got minus 18 kilonewtons. That's equal to 0. So BY is going to be equal to 18 kilonewtons minus the 7.5 kilonewtons once we move both of these terms over to the other side. So what's that going to be? That's going to be what, 10.5 kilonewtons? I'm not going to bother typing that in. 10.5 kilonewtons. Which gives us the final reaction. We can finish off our free body diagram. 6.7 kilonewtons, 10.5 kilonewtons, and yeah, so that's basically it for our free body diagram. We've solved our reaction supports. Yeah, and that's it for the question.